In this lecture, I'm going to demonstrate how to perform k-means clustering in R. I have imported the candy bars data into a data frame and labeled it My Data. The candy bar dataset contains 5 variables, the names of the candy bars and 4 nutritional facts about the candy bars. All nutritional facts are numeric variables, as you can see from the dataset. Let's cluster the candy bars into 4 clusters using the k-means clustering technique. There are a number of different ways to conduct the k-means clustering in R. In this example, we will use the PAM function of the cluster package. Let's start a new script. So first, you need to install the cluster package, and you can install it using the command install.packages followed by the name of the package cluster. If you have already installed the cluster package as I have, launch the package using the library function. You can run these 2 lines of code to launch the package. To start the k-means clustering process, we will first standardize the data because they are measured using different scales. We convert the values into z-scores using the scale function. Since we do not need to perform the conversion on the names of the candy bars, we are going to exclude the first column from the transformation, only including columns 2 to 5. And we are going to save the z-scores in a new data frame called MyData1. Now let's run it and then take a look at our MyData1 data frame to make sure that all values have been converted into z-scores. As you can see from the result, now all values have been converted into z-scores. And the data frame only contains the 4 nutritional facts: calories, fat, protein, and carb. Now we are going to use the PAM function to perform k-means clustering. A couple of things to understand before we do that. First, we need to specify the value of k in the function. In this case, the k value is going to be 4 because we want to create 4 clusters. Second, because k-means algorithm will start with 4 randomly selected cluster centers. In order for all of us to get the same results, we need to fix the random seed to 1 before performing clustering. So let's first use the setSeed function to set the random seed to 1. And then we are going to use the PAM function to perform the k-means clustering. And we are going to store the result into an object called kResult. So the function PAM, P-A-M, stands for partitioning around medoids. We will explain what medoids are in a moment. As you can see, the PAM function takes 2 parameters. The first one is the data frame with the variables, and the second one is the value of k. We are saving the clustering result in an object called kResult. Now let's first run these two lines of code and then take a look at the kResult using the summary function. By using the summary function, we are able to see the result of the k-means clustering on this dataset. Let's take a look at the results. Let's first look at the first table, medoids. So what is a medoid? In cluster analysis, a medoid is a representative observation that has the smallest average dissimilarity to all other observations in the cluster. So in other words, the concept of medoid is very similar to centroid or cluster centers, except a medoid is a member of the cluster. We can interpret the medoids as the cluster centers in most cases. For example, the medoid for the first cluster is observation number 9, which has the standardized values of calories, fat, protein, and carb of 0.8081, 0.5993, 0.7920, and negative 0.2614, respectively. Please note that these are z-scores instead of the original values. The values for the medoids help us understand the characteristics of each cluster and how they differ from other clusters. For example, the candy bars in the first cluster tend to have higher calories, fat, and protein, and lower in carb. The candy bars in the second cluster tend to have medium calories, low fat, low protein, but high in carb. Now let's look at the second section of the result, which is called clustering vectors. The clustering vector tells us which observation belongs to which cluster. For example, the first 5 candy bars in the dataset all belong to the first cluster, whereas the 6th candy bar belongs to the second cluster. Now let's take a look at the table labeled numerical information per cluster. The numerical information per cluster tells us something about the clusters. First, it tells us the sizes of the clusters. As you can see, there are 14 candy bars in the first cluster, 3 in the second, 16 in the third, and 4 in the fourth cluster. The result of the table shows us the stats about the dispersion of the observations in each cluster. As they say, a picture is worth 1,000 words. Instead of looking at these numbers, let's look at some diagrams that tell us practically the same information, but in a more intuitive way. Let's plot the clusters using the plot function. And let's run this line of code. You will be prompted to hit the return key to see the plot. Let's press the enter key. Now you see the cluster plot on the right side of the screen. The cluster plot shows you the 4 clusters and their relationships with each other. The cluster plot shows the observations using the first 2 principal components. With the first 2 principal components, we can easily see 4 distinctive clusters formed around the observations, and that helps validate the cluster structure. Now press the Enter key again to see the next plot, which is the silhouette plot. The silhouette plot shows how close each observation in one cluster is to observations in the other clusters. The silhouette width, S, ranges from -1 to +1, where a value closer to +1 indicates that the observation is well matched to its own cluster and poorly matched to neighboring clusters. Therefore, it will be ideal if all members of the clusters have S values that are close to 1. So as you can see from the silhouette plot for this cluster structure, the great majority of the observations have S values that are positive, and only 2 observations in cluster 1 and 1 observation in cluster 3 have negative S values. The average silhouette width is 0.32, suggesting that overall the cluster structure is well configured. If we want to combine the cluster structure information with the original dataset, MyData, so that you can view the cluster centers using unstandardized values, you can do the following. We can use the data.frame function to combine the cluster assignment with the original nutritional facts of the candy bars. As you can see, we are using the clustering component of the kResult object. The clustering component of kResult object contains the cluster assignment information. Let's run this line of code and take a look at the first few records in the new MyData data frame. As you can see from the result, now we have the original nutritional fact values as well as the cluster assignment of these records. If you want to see the average values for each cluster, you can enter the following command. The result shows the summary statistics of the candy bars in the first cluster. And if you want to see the summary statistics of the candy bars in the second cluster, you can simply copy this command, paste it, and then change the number for the cluster. So as you can see, in the first cluster we have 14 candy bars, and the average calories for the first cluster is 253.9, whereas the second cluster has 3 candy bars, and the average of the calories is 242.3. So these commands will show the average values in their original scales, making it easier to interpret the results. As I mentioned earlier, there are other ways to perform k-means clustering in R. For example, we can use the kmeans function. Now let's take a look at how we can perform k-means clustering using the k-means function. We need to first set the random seed to 1 so that we will all get the same cluster structure. The k-means function is going to take two parameters. The first one is the data frame that contains the standardized values for the cases, and the second parameter is the value of k. And we are going to store the cluster structure in a new object called kresult2. We're using the data frame myData1 because that data frame contains the standardized values. Now let's run this command. Okay, in order to access the information about the cluster structure, we are going to access the components of the kresult2 object. For example, the cluster component will show you the cluster assignments. As you can see from the result, the first 5 candy bars in the dataset all belong to the second cluster, whereas the 6th candy bar belongs to the 4th cluster. The centers component will show you the cluster centers. As you can see from the result, this table shows you the cluster centers for the 4 clusters in terms of calories, fat, protein, and carb. And then the size component will show you the number of observations in each cluster. So the result shows that there are 9 candy bars in the first cluster, 5 in the second cluster, 16 in the third cluster, and 7 candy bars in the fourth cluster. As you can see, the cluster structure created here is not the same as the structure created using the PAM function. This is due to the fact that different random starting cluster centers were selected for these two functions. Although there are many different ways to perform k-means clustering in R, in this lecture we choose to focus on the PAM function because it is considered one of the more robust clustering algorithms and is widely used.